Alright, good morning chemistry students. Here's a little video for you on Unit 4, Celebration of Learning Study Guide. Basically, I'll be walking through the study guide, doing some of the problems, and hopefully helping you guys get ready to celebrate your learning next week. You guys have learned a lot. Really proud of you guys. Hopefully this will be a good showing of what you guys know, and hopefully this will help you guys out. And so first, we're going to go through electron configuration because that was the first thing you learned. And remember that when we did electron configuration, I gave you guys a periodic table and I had you guys kind of annotated, right? And what we did is we kind of color coded and said that these guys here are our S block elements. These guys here in the red, we said are our D block elements. And these guys here are our P block elements. And of course, these guys here are the F block, but we said we're not really going to worry about that. And so yeah, these are our elements. Sorry, this is how we divide up the periodic table. And so if you don't have something like this, please make sure that you do annotate your periodic table, because this is a really helpful way of helping you do electron configuration. And so please do annotate up your periodic table. If you need one, please ask me, and or print out one for yourself. Yeah, annotate it up like this. And then one other thing that I did want to point out was where we also mentioned that the period numbers here tell us the number of rings / energy levels. And so for example, if we have a element in this 5th period, it's going to have 5 energy levels. It's going to be at the 5th energy level. The one thing, though, to note is that for D block, it's going to be period -1 for the energy level. So, for example, here, something like TC, right? It's the 5th period, but so its D orbital is going to be not at the 5th energy level, but 5 - 1. So it's going to be at the 4D. It's going to be the 4D orbital at that point. But anyways, do annotate it up like this, and so I'm going to use this a lot as I walk through these guys for you guys. And so 1A, for example, the electron configuration for S, we take a look and we see, okay, this is in the 3rd period P block, right? So what we know is that we're going to end with 3P. It's going to be specifically 3P1, 2, 3, 4, 3P4, right? But remember, Aufbau's principle, the building up principle. In addition to having, right, that 16th electron in the 3p orbital, we also had a bunch of other orbitals, and we put electrons inside of those orbitals, right? Specifically, we had everything up until 16. And so what we can do is we can move from left to right, reading it off the periodic table. And so what we can say is, okay, well, to get to S, which is 16, we had to have put 1 and 2 electrons inside. So we say, okay, first we had the 1, this is green, so it's 1s, we put 2 inside of the 1s. And remember, that's all you can put inside of the sunny rooms, if you remember the analogy, little activity we did at the beginning. And so we have 1s2, and then 2nd period S, 2s2. Then we come here, P is going to be 2p, 1, 2, 3, 4, 5, 6 electrons in there. So 2p6. Here, 3s2. And then we get here 3p4, as we mentioned, right? And so if you follow this method and you kind of just read, increasing in the atomic number, so you go from 1 to 2 to 3 to 4, right? You keep going. You will end up at once you end up at your element, you will have filled up all the orbitals getting up to that element. And so therefore you're following all the rules, you're following Aufbau's principle, you will be following all the other little rules that we had. And so that's how I'm going to be doing these. I'm not going to do all of these because it'll be a little bit annoying for you guys to watch through. But yeah, let's do a couple other ones. So for example, let's do C. Right, to get to C, we will have had to go from here to here to here. So that would have been 1s2, 2s, 2, 2p, there's 1, 2. So that's going to be 1s2, 2s2, 2p2. Let's skip ahead to CR. Okay, so let's skip ahead to CR. So to get to CR, we would have needed to fill up 1s2, 2s2, 2p6, because 1, 2, 3, 4, 5, 6, 3s2, 3p6, we're going to fill that up, 4s2, and then remember here, you might want to say 4d, but remember, for d block, it's going to be period minus 1, so it's not going to be 4, it's going to be 3. 4 minus 1 is 3. To get to CR, we have 1, 2, 3, 4. 4 electrons will have gone into the 3d orbital. So let's put that in. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And I'm sorry, that should be here for CR. But yeah, so that's how you do CR. Let's do one other one. Let's do iodine, because that's a little bit hard, or it's long, right? So to do that, we're going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can put up to 10 electrons in the d orbital. If you forgot that, then just count. All right, so 10, back to 4p6, 5s2, 4d10, 5p, 1, 2, 3, 4, 5 electrons in that 5th orbital. So for I here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and we said 5s2, 4d10, and then 1, 2, 3, 4, 5, 5p5. There you go. Cool. So that's iodine. Sorry, let me try to straighten this out. There it is. Cool. So that's iodine. And then here, you might not be able to see this very well on video, but this is actually an ion. It's Cl minus. And so the way that we do ions, remember, is I want you to first write out what the normal configuration is for it, and then either remove or add an electron to the valence orbital, or to the next highest energy orbital available. And so let me explain. So first, let's just do it for Cl, and then we'll deal with the minus here. So Cl is going to be 1s2, 2s2, 2p6, 3s2, 3p5. So 1s2, 2s2, 2p6, 3s2, 3p5. Okay, now the minus, remember, minus means that we added a negative, okay? So minus means we add a negative, which is really what we're saying is add an electron, right? So we're going to add one more electron. Where are we going to add that one more electron? Well, we're going to add it to the highest energy orbital available. Remember, if we want to kind of visualize this, right? Basically what we have here, this is like the 3p subshell. We have at the moment 1, 2, 3, 4, 5 electrons in that 3p. We have room for one more, and so we're going to add it here. And so we're going to add it here, and so we're going to make this really not 1s2, 2s2, 2p6, 3s2, 3p5. We're going to make it 3p6 at the end. And so I'm just going to put that in here. This is your answer. Okay, so that's how you would do that. And then let's just do one here for K. K is going to be, this is K positive, okay? So K positive, that instead of adding a negative, right, we're actually going to be losing a negative. So we're going to be losing a negative, which means we're going to be losing an electron. And so to do that, we are going to first write out the full configuration for K. K is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So now what we're going to do is basically we're losing a negative. We're going to be losing from the highest energy orbital. And so it's going to be this guy. This guy is going to be lost. We're going to lose this electron, and therefore we don't need to write the 4s anymore. Basically, that doesn't really exist since it's empty. And so we're going to have this. And so this is going to be its configuration. Now you may notice that Cl- and K+ have the same configuration. And that configuration, actually, interestingly enough, is the configuration of AR, right? AR is 1s2, 2s2, 2p6, 3s2, 3p6. And so what we say is that these are isoelectronic. And this is not coincidence. This is, in fact, a trend. What we're going to be learning in Unit 5 is that everyone kind of envies the noble gases. They want to be just like them. And so this is one of the results of it. Everyone wants to have the configuration of a noble gas. The noble gases are ideal. They're kind of like that one friend who has their life together. You want to be like them. And so Cl and K are both trying to become like that, get their lives together. And so, yeah, they're going to have the same electron configuration as AR and as each other. So, interesting little thing. You don't have to know that for this celebration of learning. You don't need to know isoelectronic, but hey, chemistry, kind of cool. Lots of things going together. And you guys are learning so much, and so you guys are understanding this. This is wonderful. But so, anyways, all that to say, let's keep going. And let me show you guys a couple interesting ones, especially I want to show you guys 3 and 4. But before we do that, let's just go over abbreviated noble gas electron configuration, right? Basically, as we could see with something like I, that's kind of annoying to write out, right? It's a lot of stuff. And so what we're going to do is we're going to use the abbreviated / noble gas electron configuration to make it shorter and easier for us. And the way that you can do this is to basically, or the theory here at least is, we're going to use the noble gases as our checkpoints of sorts. So instead of writing out, for example, Al, for Al we would have to write a 1s2, 2s2, 2p6, 3s2, 3p1. We can instead say, well, the electron configuration of Al is basically just the electron configuration of Ne, and then also 3s2, 3p1. So let me kind of do that for you guys, right? Al, its configuration is basically going to be the configuration of Ne, and then also 3s2, 3p1. Now you might be saying, what the heck, how does that make sense? Well, think about it like this. What's the full configuration of Al? We just said is going to be 1s2, 2s2, 2p6, 3s2, 3p1. Okay, well, what's the configuration of Ne? The configuration of Ne, right, is going to be 1s2, 2s2, 2p6, right? That's Ne ends of 2p6, right? And so do you see, right? Basically, this thing here, right, is just this thing here, right? And so the way of us writing configuration or shorthand is this. So configuration of Ne is this. And so what we can do is just say, well, just put this here and then also have this on. And that's what we did here, right? Do you see? So that's how the logic here. We're just basically replacing. So yeah. So that's how you do that. Another kind of shorthand for it is just take the noble gas in the row above. So for example, for Al, it was Ne, and so write that, and then just from there continue on in your electron configuration. So for example, for N, it's going to be He, right? That's the one above. And then also 2s2, 2p6, 2s2, 6, 2p3, right? And so, yeah, Na is going to be, the one above it is Ne. So it's going to be Ne, and then after Ne, we go to just 3s1. So that one was actually really easy. And then Ne, what's the noble gas configuration of Ne? Well, what's the noble gas above Ne? Well, you could do, I guess you could say He, 2s2, 2p6, and so that's okay. You could do that. Or you could just say, well, the noble gas configuration of Ne is just Ne, right? Yeah, I mean, that's technically correct as well, right? And so you could do that as well. Pretty easy, right? Right? Why would you do this? This tells you nothing, but we don't really use noble gas configuration for noble gases, but I just wanted to throw that in there just because it's technically good. Cool. Okay, so let's go on to some interesting ones. Number 3 and number 4. This is where, kind of advanced level questions where it's like, okay, what is the electron configuration of carbon? Well, there's different ways of writing it, right? So if I asked you, hey, what's the electron configuration of carbon? And I'm not being specific, okay? I didn't say what's the full. Right here I said full. Right, and here I said abbreviated noble gas. But if I just say what is, right, one student says 1s2, 2s2, 2p2. And, if you look at that, it's like, okay, 1s2, 2s2, 2p2. Well, yeah, that checks out. But another one says it is He, 2s2, 2p2. And so they're like, hey, it's He, the configuration of He, and then also 2s2, 2p2, which also that makes sense. The question is, who's correct? Or are both correct? Or are both incorrect? Explain your reasoning, right? And so what I want you guys to see is that they're actually both correct, right? These are both the electron configuration of carbon. If it's not specific, you could put either. And so these are both different ways of writing it. And so what we say is they're both correct. Student number 1 gave the full configuration Student number 2 gave the abbreviated / noble gas configuration. In the absence of kind of a specific request, you could give either. Hey. So that's one example, and here's another example. What if I asked which element has the following electron configuration? Okay, so last time I said, hey, what's the configuration of carbon? This time I'm saying, what's the configuration? What element does this match up with? 1s2, 2s2, 2p6. One student replies, oh, that's the configuration of Ne. While another replies, oh, that's the configuration of Na+. And a third student replies, Cl-. Who's correct? Or are both correct? I shouldn't put both. Or are all correct? Or are all incorrect? Explain your reasoning, right? So, who's correct? Well, you look at this and you're like 1s2, 2s2, 2p6. Well, that's 1s2, 2s2, 2p6. That is Ne. Yeah, so student number 1 is correct. Na, well, okay, Na is 1s2, 2s2, 2p6, 3s1. But remember, this is Na plus. And so we actually take off this electron that's in 3s1. And so we actually just end up with 1s2, 2s2, 2p6, right? Do you see? Right? So Ne is 1s2, 2s2, 2p6. Na plus is 1s2, 2s2, 2p6, 3s. What? We take off that. We take off that, electron because it's the ion, and so that's also correct. And then the last student says Cl-, right? So this is Cl-, and we see that the configuration of Cl is 1s2, 2s2, 2p5, but we add on one electron here and make it 6, and so actually all 3 are correct, right? All 3 are correct. Because, yeah, the correct configuration of these is all 1s2, 2s2, 2p6. So this configuration belongs to all 3 of these. Again, what we can see is that these are isoelectronic. They all have the same configuration. Again, going to be important for us in the next unit. But yeah, so some interesting one. Ground state, remember, ground or excited state. How you want to think about these ones, the excited state is when we're basically breaking the rules, when we have an electron that's gone to a higher energy level than it otherwise would be. This was the explanation for the fireworks, where we said, if you add in energy, then it's possible to go up to a higher energy level. And so, I'm sorry, I put a typo in here. This should be 3p1. I'm going to change this for your, when I pass it out to you guys. But so basically we have O here, which is 1s2, 2s2, 2p3, 3p1. And so how you want to think about it is to first say, okay, well, ordinarily, what would O be? Ordinarily, O is going to be, and I'm going to draw this actually for you. So it's going to be 1s, 2s, 2p. Remember, O's configuration overall is 1s2, 2s2, 2p4. So it's going to be 1s2, 2s2, 2p4. And so it should look like this, right? But what we're saying here is it's not going to be 1s2, 2s2, 2p4. It's actually 2p3. What happened to that extra electron? Well, what must have happened is it must have gotten excited. There must have been an influx of energy that resulted in it going up to the 3p level. And so what we're saying here is that this must be in an excited state, because the electron, this electron, is at a higher energy level than we otherwise would expect. It's at the 3p, and so this must be excited. Okay, since that electron is in the 3p orbital. Cool, okay. Consider the element Cl. What is its electron configuration? So I'm not gonna, actually fine, I'll write it. I just don't want this video to be too long. But so I'm not gonna explain again how to do electron configuration. I'm just gonna write it out. 1s2, 2s2, 2p6, 3s2, 3p5. The abbreviated noble gas configuration here is going to be Ne, and then it's going to be 3s2, 3p5. And the reason, just going over these quick, but I want to show you the orbital diagram again, right, is remember, just basically draw it out where we have 1s, 2s, 3p orbitals always. We're going to have a 3s and a 3p. Remember, the orbital diagram we're not drawing orbitals. It's a diagram, not an orbital picture. And so, yeah, and remember your rules, right? Go back and review that little activity that we did with the sunny rooms and the pink rooms and placing borders in there. But so, yeah, we have 2 in the 1s, we have 2 in the 2s, we have 6 in the 2p, we have 2 in the 3s, and then we have 1, 2, 3, 4, 5 in the 3p. Remember the seats on the bus rule, don't double up unless you have to. And so, yeah, this is what its orbital diagram is going to be. All right, a couple more. Which element has the larger radius, C or F? Explain using Coulomb's law. And so, please, 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 on celebrational learning, do not just say the correct answer is going to be C is larger, but don't just say, oh, because it's more to the left on the periodic table. Yeah, that's true. But why is that, right? What we want to understand is the underlying trend. Remember, we did all that activities with Coulomb's law, right? That it's really key that you understand this. It's a hugely important concept for physics, for AP chemistry. I really want you guys to know this. And so, which is larger, C or F? C is larger, right? Because although C and F both have the same number of rings, right? C and F both have the same number of rings. And so you would say, well, C and F, right, they both have 2 rings because they're both at the second period, right? C and F are both at the second period. But what's going to happen is C is going to be larger because it has less protons. C only has 6 protons. F has 9 protons. And so F basically, has a positive 9 charge in that center, whereas C only has a positive 6 charge. And so, and remember the electrons, each of them have a -1. And so basically what we're doing is we're attracting, right, like a -1 here with a positive 9 versus a positive 6. The positive 9 is going to be able to attract much more and therefore close in its rings. And so I'll write out a full explanation for your key. But yeah, it's going to be C. C is going to be larger. It's going to have a larger radius. Cool. Okay. Similarly, ionization energy is actually just flipped. And so which one has the larger ionization energy? It's always going to be the smaller element that has a larger ionization energy. And so F has larger ionization energy because remember, if you have a smaller atom, what's going to happen is, and I'm going to exaggerate this a bit so you can see it, right? If you have a smaller atom, this atom is going to be able to hold on to its electrons better because of Coulomb's law. Distance is less. There's less distance here between the positive center and the electron, and therefore it's going to be able to hold on to it better. Also, you can make the argument of +6 versus +9. +9 is going to be able to do a better job again of holding on to its electrons. And so F has larger ionization energy. C is larger, has larger radius, but it's inversely correlated with ionization energy. Ionization energy for F is going to be larger. Again, I'll write a bigger explanation for your key, but just in the interest of making this video short, I'm going to continue on. Okay, so then let's go on to let's go on to light kind of questions. And remember, there's two key equations that you need to use, which will be given on a celebration of learning, but you do need to know how to use them, right? So E is the energy, E is equal to HF. E is energy, H is equal to Planck's constant. F is equal to frequency. Here, C is the speed of light. Lambda is equal to wavelength. And F is equal to frequency. And so, yeah, what we can do is we can just plug into these equations. And so what is the energy of red light, which has a wavelength of 700 nanometers, or 7.0 times 10 to the negative 7? What you're going to have to do here is, here we're given wavelength, which is lambda. So lambda is equal to 7.0 times 10 to the negative 7 meters. You're going to have to take this and plug it into this equation, right? You can't plug it into here because you have to plug it into here because this is what has lambda. And so you're going to plug it into here. You're given C, right? Speed of light is 3.0 times 10 to the 8 meters per second. And so you have these two things. So you can solve for this. But you might say, why would we do that? Well, if you have frequency, then you can plug it in to here, which then will get you energy, right? And so it's actually a very interesting thing to note that frequency is shared by both of these. And so because it's shared, right, if you solve for it here, you can put it into here. And so I'm actually going to pause this video because I got to go make these copies for you guys. But I'll make a part 2 video where I'll actually plug this in. So stay tuned for part 2.